Okay, so in this particular lecture, we are going to take a small deviation, and we have covered a lot of theory. We have done a lot of theoretical work, lot of analysis using scaling arguments, using integral methods. Also, we have talked a little bit about that how you can solve certain things wholly numerically. But at the same time, as students, one might get the feel that we hear a lot about this wall heat flux, wall temperature. Based on those parameters, you calculate the Nusselt number and things like that. Then how do you actually in real life measure some of these events? Okay, because the theoretical analysis that we have shown are mostly for canonical problems. That means problems which are very simple in nature. Now, real life, as when we started convection heat transfer, we actually said that the real life is very complicated. That means you get complicated situations like cavities, then gas turbine blades. Okay, we considered many applications from small scale to very large scale, and we saw that analysis becomes progressively more and more onerous when we actually deal with problems like that. So, our idea over here now is basically to come up, to give you guys a flavor, that how do you actually measure this wall heat flux, how do you actually measure the flow, how do you actually measure the convective heat transfer coefficient, right, or in other words the Nusselt number. So, there must be some measurements, because all these numerical exercises that you do need to have an experimental validation, right. So, unless you have an experimental validation, your numerical work does not make much of a sense, especially in complicated situations where no analytical solutions may exist, right. So, based on this, here in this particular section of our lecture, we are basically going to cover a couple of techniques. Basically, one will be the thermochromic liquid crystal based techniques to measure heat transfer. The other one will be using IR thermography, that means infrared thermography. Okay. So, there are lots of other techniques as well. You can use laser induced fluorescence also, for example, to measure the temperature field. Okay, it is possible to do that. You can use the garden variety thermocouples also, because in many applications you do need thermocouples, like for example when you want to measure the temperature you use thermocouples, but thermocouple you guys already know, so there is not much to talk about thermocouple, that how a thermocouple responds. And thermocouples mostly are point measurement techniques. That means it will give you the temperature at a particular point in the field. They are not field measurement. That means you don't get to see the temperature field across the whole domain. You get to see the temperature at a particular point in a particular domain. Okay, so that is thermocouple, but thermocouple is extremely useful. Okay, but with time people have thought that why not go to some more sophisticated techniques which gives you more idea of the field. Like for example, you want to watch a movie, right? So it's like in a movie that you want to see everything. Okay, you just don't want to see a point, right, what is happening at a point, because that may not be the unique descriptor. You want the full spatial information, how the temperature field is spatially varying, and things like that. So, thermocouple is we are not going to cover, but that you can find out in any of your UG courses that you may have taken, that what is a thermocouple. The ancient form of measurement will be the thermometer. Like for example, when you want to measure your fever, how do you do it? You just insert a thermometer under your armpit or under your tongue, and you see that what is the temperature, right. That is a crude measurement technique, because it is an equilibrium measurement. Okay, it takes a lot of time to steady it out. So, essentially you do not get any fluctuations or anything like that. Okay. But that is a very useful thing that you use at home. In home you do not use an IR thermography or any other sophisticated techniques, because it is not required, right. So, the idea of any measurement technique is that what is your requirement. Okay. Like for example, when you want to measure the body temperature, thermometer is an excellent choice. You do not need anything else, right. But when you try to measure, for example, the temperature profile over a gas turbine blade, thermometer is not going to do, because you are going to have a lot of fluctuations in the temperature field, near and on the blade. So, therefore, there the thermometer is not a useful instrument, because its response time, is extremely large. So, you are going to basically erase away all the fluctuations, and you are going to get some kind of a misleading kind of a value. So, we are going to take two interesting measurement techniques about which you may not have heard so far. So, first one of them, if you look at it here, is going to be the thermochromic liquid crystals applied to heat transfer. That is the first technique that we are going to discuss. This is just going to give you a bird's eye view, because this is not meant for an experimental engineering course, but this is just to give you an idea so that you can kind of correlate that all this T, Q prime and all these things that we have heard so far, okay, in the course, that has got some meaning attached with it, right. There is some meaning attached with it. This is how you can actually physically measure the quantities, right. That is the most important part. So, if you look at the slides now, okay, you will find that what are liquid crystals. Now, liquid crystals is something that you already know, right. Liquid crystals, you see it for example, in LCD TVs are usually made out of liquid crystals, right. So, liquid crystals are basically highly anisotropic fluids that exist between the boundaries of the solid phase and conventional isotropic liquid phase. So, it is neither solid nor liquid, it resides somewhere in that boundary, right. Thermochromic liquid crystal, okay, visualization actually depends on some of the interesting properties, okay, which is called cholesteric properties of the liquid crystal to reflect definite colors at specific temperatures and viewing angles. This is the most important part, right. How does this technique actually work? Okay. If you look at this particular example over here, you will see this is a crystalline solid, well arranged, right. This is a liquid crystal, and as you go on increasing the temperature, this is an isotropic liquid. Okay. So, there is some order in the case of a liquid crystal to begin with, and based on their structure, they can actually reflect light at certain definite colors and at certain temperatures. Okay. So, that property can be now used to perform certain meaningful tasks. So, let us see. Okay, this is part of the introduction. So, you can see the phase of the matter that exists between solid and liquid phase. It may not have any positional order, but some orientational order. Okay. So, there is some orientation, basic orientation that you will have. It is an anisotropic material. Okay. So, in the cholesteric phase, the molecules in different layers. So, these are the different layers if you look at it, right. You see that? These are different planes basically. They orient at slight angle with respect to each other. The first layer has got a very different orientation from the second layer. The third layer has got in turn a different orientation than the fourth layer, and so on and so forth. Okay. So, there is a gradual change in the orientation of the arrangement as you go from layer to layer, right. So, in each consecutive layer, the molecules are oriented slightly off with respect to each other. Okay. So, this is visualized as a stack of very thin 2D layers, okay, with the director in each layer twisted with respect to the one that is above and below, right. So, this is like a stack, it is like a stack, it is like a 2D stack of many layers, right, where each of the layer, the first layer is slightly twisted with respect to the one at the top and at the bottom, right. So, that is the most important part if you look at it. Okay. So, in this structure, the directors actually form a continuous helical pattern, okay, which is called the pitch. So, if you take the director, that means all these layers are at an angle, right. This may be the angle for this may be the angle for this may be the angle for this, right. Okay, this may be the angle for this is the angle for this is the angle, this is the angle, and this is the angle, right. So, if you plot kind of the directors, that means the direction in which they are actually oriented, if you plot them, you will find that there is a repetitive pattern that actually emerges, okay, and they are arranged in a helical pattern. Okay. So, this particular repetition cycle is what we call the pitch. Okay. The directors actually form a continuous helical pattern about the layer normal. Okay. So, the orientation of molecules in a cholesteric liquid crystal is given like this. This is the pitch. Okay. This is the pitch. This is what is called the pitch from here to here. This is the pitch. Right. After that, it returns back to its original configuration. Okay. So, understand, it is like a slight twisting that happens, and then again it goes back to its original configuration. Okay. So, it has got a pitch because of mainly the ordering that it has at each of the individual layers. Okay. Okay. Now, the pitch P is defined as the distance it takes for the director to rotate one full turn in an helix. So, as it turns, so it just takes the time for it to complete one full cycle in a spatial sense. Okay. Now, due to the helical structure of the chiral nematic phase is its ability to selectively reflect light of wavelengths equal to the pitch length. So, whatever is a pitch length, right, this kind of crystals can actually reflect, selectively reflect light whose wavelength are equal to the pitch length, right. So, these 2D layers, right, they, as we said, that they have a pitch. So, there is a helical pattern, right. So, that helicity actually repeats. So, once it takes one full rotation or one full turn in that helix, okay, after that it starts to repeat itself, right. Okay. Now, that smallest block, okay, that one full rotation, that distance is called the pitch, right. Once we know what is the pitch, okay, of that particular system, right, it is the ability, it can actually reflect light of that particular pitch, wavelength equal to that particular pitch. Basically, lambda is equal to that pitch, right. It can actually emit light, reflect light of that particular wavelength. Okay. Now, what happens is that when we change the temperature in such crystals, right, the pitch length changes, right. As we change the temperature, the pitch length actually changes, resulting in an alteration of the wavelength of the selected light, reflected light according to the temperature. Okay. So, decreasing the temperature increases the pitch length, okay, whereas increasing the temperature decreases the pitch length. So, that is the two things that actually happens, right. So, as you decrease the temperature, the pitch length actually increases, that means the light that it reflects actually now has got a larger wavelength or a longer wavelength, okay, and the pitch also changes when we actually increase the temperature. So, it goes the other way, so it decreases. So, the wavelength of the reflected light can be also adjusted by changing the chemical composition of these liquid crystals. So, you understand the basic thing, these liquid crystals has got some arrangement, some order, right. These orders, okay, they are arranged in some kind of a helical pattern. Of course, the pitch is very small, okay. So, depending on this pitch, depending on this orientation, okay, it is able to selectively reflect light of a certain wavelength, right. Because it is able to reflect light of a certain wavelength, if you change the pitch, you change the wavelength of the reflected light, right. It is a simple thing. So, that means with temperature, if the pitch changes, then the wavelength of the reflected light will also change, right. So, temperature leads to a change in the pitch, leads to a change in the wavelength of the reflected light, right. So, there is a connection between temperature and the wavelength of light that is reflected, right. So, this is what can be controlled also by using chemical composition. So, the simplest implementation of this, okay, if you have seen, and this is quite common in foreign countries, that you have this what we call this mood rings, right. So, mood rings are basically rings that you wear in your finger. So, basically why it is called mood ring, because if you are angry, your body temperature changes, the color of this mood ring also changes. Similarly, if you are very depressed, your body temperature changes, therefore, the color of your mood ring also changes. Okay. So, depending on your mental state, if that leads to a change in your temperature, in the body temperature, okay, these mood rings actually have this thermochromic liquid crystals. So, their actually pitch changes, their color changes as a result. By looking at your mood ring, right, people can make out that whether you are happy or you are sad or whatever, right. Similar things you have in color sensitive coffee cups, right. If you see in certain coffee cups, you will see when it is hot it is red, and as the temperature comes down you will see a gradation in the color, right. So, these kind of coffee cups also demarcates that when you are trying to pick up a coffee, you know that it is red, that means it is hot. Okay. Similarly, when you are picking up something else, I mean when it is cooled down, the color will change to something else. So, just by looking at the color you can kind of see that which one is hot, which one is cold, right. So, that is an interesting thing. Okay. So, it is also used on heated surface. Sometimes sometimes the doctors also use this thermochromic liquid crystals on your forehead to check the temperature. As it comes onto your forehead, it changes the color. So, if you calibrate it well enough, you would be able to make out that what will be the body temperature of yours. Okay. So, however, these are the simplest implementation, okay, which does not require much of an effort. Okay. Advanced implementation, which is research quality thermograph, that means which you are going to use to calculate the temperature, right, as in the case of your Nusselt number, you need a heated surface, you need a calibration, because the color and the temperature calibration has to be done, right, because you know the color that is coming out and you know the temperature. So, a priori you need to have a calibration done, okay. And you of course need image acquisition and other softwares, and you need high resolution thermography images basically to visualize and make out that what these colors are actually telling you, okay. So, the TLCs, the color changes from red to violet with increasing temperature, some of the properties, okay. Clear when it is above and below a certain active range. So, these TLCs has got active ranges. So, if your temperature is too high, it will blank out. If your temperature is too low, it will blank out. So, only over a certain range, that range could be 20 degrees Celsius range, could be 30, could be 40, that is where it changes its color from red to violet with increasing temperature, okay. There is an active range and band range depending on the composition, okay. It is repeatable and reversible as long as it is undamaged. That means once you take the temperature out, the color will return back to its normal, okay. So, you can again use it again and again. So, it is not a one time use and throw kind of thing. It has got a quick response time of the order of 10 milliseconds, which makes it a very attractive proposition for certain experiments, not for all, because 10 milliseconds still is a very high time if you are dealing with very turbulent flows and things like that. But for many applications 10 milliseconds can actually be a good thing to do. Can be painted on surfaces or suspended in fluid also. This is a very interesting point. Can be painted on surfaces means this will enable you to gauge the surface temperature, which is paramount importance when you are trying to find out your Nusselt number. You need to know your wall temperature, right. It can be also seeded in the flow. That means you just seed it into the flow field and it will light up and show you the temperature of the flow field, okay. So, you can actually do that also. So, okay, there are both ways by which you can actually get this done. In the past, okay, quantifying the color was difficult and ambiguous, and TLC was used as a qualitative measurement only. That means when we say red, right, when a human eye sees red, right, okay, you might want to ask, what do you mean by red? Red is a very qualitative color, right. What is dark red, darkish red, lightish red? You can have, we tend to grade it based on what our eyes can perceive, right, but you need more quantitative information than that, right. You need to know exactly what red are you talking about, right. So, recent advance in the digital image processing allows for quantitative and fast measurements, and inexpensive systems can be used. Basically, all you need is a very high quality RGB camera, okay, and the TLC crystals and the TLC sheet, okay, that is it. So, pure liquid crystal materials are thick, viscous, greasy, and it is very difficult to deal with under most heat transfer conditions, okay. See, these materials are also sensitive to mechanical stress, right. So, micro encapsulation is a procedure by which it encloses the small portions of the liquid crystal material in a polymeric shell, okay. It actually solves the problem of stress sensitivity and chemical deterioration, okay. So, there has been lot of work. If you ask any polymer person or chemical engineers, okay, they will show that how this encapsulation process actually happens for liquid crystal and how they can be actually used to, you know, use it in common heat transfer applications, because as we say, pure liquid crystals are thick, greasy, viscous type of fluids which are not very conducive, okay, to the measurements that we are dealing with, okay. So, let us look at a sample graph. So, this is for example the reflected wavelength, this is the temperature, this is the relationship between temperature and wavelength, okay. So, the TLC is what it does, it modifies the incident white light. So, you are going to shine white light on this particular TLC coated object, right, and the color changes smoothly as a function of temperature, that is it, that is what happens, right. So, you shine white light, it selectively reflects particular colors, which is what you see. So, the color changes in color play interval is shown in the figure, okay. In this particular figure you can actually see it, okay, where you can see that is a highly nonlinear process, by the way. You can see that nature of that graph is not a linear graph that you slowly move on in the color spectrum, right. So, it is a nonlinear graph, as you can see from the nature, right. It goes from violet all the way up to blackish, and violet from red to violet and then black, okay, but depending on, but it varies in a nonlinear fashion, right. So, that is what it is, right. So, and the range is somewhere between anywhere between 700 to 400 or 350 in that nanometer range, that is where the change actually happens, right. So, this is a sample color spectrum. Depending on temperature, we know that what is the color that it actually reflects, right. Okay. So, the relationship between the color and between the temperature of the crystal and the measured hue of the reflected light defines the calibration curve. Okay. So, this is the hue. Okay. The color established using calibration plate of known temperature distribution. As I said, it is a nonlinear relationship, accuracy varies with color, okay, and this is one of the sample curves that we have shown. Okay. So, the qualitative measurement to quantitative measurement, what we want to do is basically you want to go from a RGB type of model. RGB is the red, green and the blue channel that any cameras will have, okay, to an HSI kind of a model. Okay. So, in the HSI color model, the hue of the reflected light is basically a function of the temperature. So, the RGB image is first converted to an HSI image, and the hue value of each pixel indicates the temperature of the corresponding location. Understood? So, first you get an RGB image, you convert that to the hue format, and the hue at each pixel, the image that you take has got these pixels, right. So, that is the lowest resolution or the minimum spatial resolution that you can get. So, there if you calculate the value of the hue, that will correspond to the temperature of the surface. Okay. So, RGB basically what it has is that it has got 3 primary colors, red, green and blue. All other colors are obtained by combining, by just mixing these colors. HSI model was designed keeping in mind the graphic designers and artists think of color. Okay. So, artists use terms like saturation, right, which is called the pureness of a color, right. Hue, the color itself, and intensity is the brightness of the color. This is what an artist would actually use, that is why it is called HSI model. Okay. So, hue is the color in itself, saturation is the pureness, and I is basically the brightness of the color. Okay. So, the RGB or the red, green, blue in this model, the primary colors are red, green and blue. It is an additive model, that means all other colors are basically added. So, in the RGB color space, if you look at that, say for example, the color with a P are the primary ones. Okay. The dashed lines, okay, the dashed lines indicates where to find the grays going from 000 all the way up to 255, 255, 255. This is the range that we have. Okay. Now, in the HSI model, in the model luminance or intensity is decoupled from the color information, which is depicted by a hue and a saturation channel. Okay, this model is suitable for interactive manipulation of the color images. All softwares actually do it. So, hue is the actual color. It is measured as an angular degrees around the cone starting and ending at red. So, this is how the hue is actually. So, it is like a cone. So, this one was like a cube. Okay, this is like a cone. So, hue is basically the angle. So, you start from red, end at red, and you pass through all this kind of color. Saturation is the purity of the color measured as percentage from the center of the cone to the surface. Okay. At 0% saturation, the hue is basically meaningless, of course, that is at the center. Intensity is measured in percent from black to white. At 0% brightness, both hue and saturation are actually meaningless. So, brightness is basically the height. So, you understand, this is like a cone. Okay. The angle of the cone, okay, this particular rotation basically designates your hue. The center to the edge distance is basically governs your saturation, right, while the distance from the top to the apex of the cone is basically what designates your brightness, right. So, this is like a cone type of a model, and this is the conversion factor, that what is the intensity, hue and saturation, how they are related to the RGB. So, remember RGB is basically an additive kind of a model, right, with 255, 255, 255 being the maximum. Okay. So, it has got basically 3 channels. HSI model on the other hand operates on like a cone type of a framework, okay, and the relationship between RGB and HSI are given in that particular fashion, right, what you see, okay, at the left. So, you can see that intensity is 1/3 of R plus G plus B. Okay. So, let us look at a very typical experiment. So, now you know that you get the color, you can get the hue, you can get all those things and you can calibrate with the temperature. So, you know how this calibration thing works, right. So, let us look at a very typical experiment. Okay. So, this measurement is inside a convection box, okay, the temperature cavity. This is where you want to measure the temperature, okay, and the flow field is illuminated with a 2 mm sheet of white light, okay, halogen light or xenon flash lamp, and these are observed in a particular direction. It has got a 3 chip CCD camera and a 32-bit frame grabber. These are all technical details, you do not need to know that much. Okay. So, if you look at the density of the TLC material, so if you look at this kind of a flow, this is like a natural buoyant flow, okay, that you can see in this particular picture. Now, if you can see, so this one is that you can see the rotation, that is you can see how the full flow field is actually working. At the same time you can see the color ranges. So, here it is red, here it is more bluish, right. So, you know the image shows natural convection and here you have used unencapsulated tracer particles, okay, and you can actually see what the flow field and the temperature actually looks like. So, in one shot you get the information about the temperature as well as about the flow field, okay, in one single snapshot, right. So, you know what the temperature is, red to blue. So, you can say which one is hot, which one is cold, right. Okay. At the same time you can also see the direction, that means how this flow field actually happens. So, with a thermocouple you would have never got this kind of a thing. Okay. Okay, the transient method, the TLC is also used to measure the surface temperature of a test specimen while determining the heating time. So, that means you can record the rate of heating, okay, by monitoring the color change pattern. So, you just take pictures of the color, then you convert that to a temperature and you can find out what will be the temperature history, right. You can also use the steady state method, that means you want to measure the surface temperature, okay, using say a local heat flux. So, if it is a constant heat flux kind of a situation, right, you want to measure what is the surface temperature. So, you can also use a very similar method like this. Okay. So, these are more sample data, say for example, this is a surface where TLC sheets have been pasted and you can see the temperature distribution, you can see all the temperatures, okay, marked out. So, with very good resolution you have been able to get. This is heat transfer in narrow channels, okay. This is for example water impinging on a TLC coated surface, okay. This is freezing of water in a cavity. So, you can see all kinds of things, okay, has been captured using the TLC based technique, right from surface temperature all the way up to freezing, okay, all the way up to impingement. Okay, got it. So, advantages is that flexibility of use in virtually any temperature measurement, okay, and it has got ultra high, less than a micron order spatial resolution, non-destructive in nature. You can use common color cameras, that means DSLR cameras and other things can be useful, okay, and it is a low cost things, okay, low cost than any other system that we can do, okay, enable live test, but you can see the temperature distribution also, right. There are certain deficiencies as well. It is not a very quick tool because you know the response time is still about of the order of tens and hundreds of milliseconds, and for very large surface or with very large temperature differentials, if the delta T is very large, this cannot be used because the band of operation is actually normally very restricted, 20 to 30 degrees Celsius. So, in the next class what we will look at is another measurement technique which is called IR thermography.